In this video, I'm going to explain why the triangle angle sum, meaning if you add up all the angles in a triangle, all three of them, they always add up to 180 degrees. So I'm going to show you or prove to you why that always happens using some parallel line concepts here, okay? Now the good old days here, I might ask you to grab a protractor. I'll go ahead and do this one. And let's just measure the three angles and see if they add up to 180 degrees, right? So I'm going to take my protractor here. I'm going to set one side on the 0 line here. So here's my 0 line. It opens up 10, 20, 30. So if I measure this angle, it looks like this angle would be at 100, and I'm going to go with 107. Okay? So this angle looks like it's 107 degrees right here, right? It's obtuse, bigger than 90 degrees, right? So if that's 107, if all three angles add up to 180, so 107 plus this angle equals 180, then if this is already 107, then doesn't that leave the sum of this angle plus this angle to be 73? Because 73, right, if we add these two up, 73 plus 107 is 180. So if we know that they have to add up to 103, then really all that I have to do is measure this another angle. Doesn't matter if it's this one down here or this angle up here, but all we have to do is measure an angle, and we'll use the sum to find the third one. We'll just measure it to check it. So anyways, let's measure this second angle here. So if I do that, it looks like this angle is right at, we'll go with 40 degrees. So this angle measures out to be 40 degrees. So we automatically know what this angle can be now, right? 107 plus 40 is 147. So if we subtract that from 180, subtract, the two we know from our sum, it's going to leave us with the angle we don't know. So 180 minus 147 must be 33 degrees. And let's just check it with our protractor here. Okay, so rotate this. I'm going to put this right on the vertex. We'll rotate so our 0 line's perfect. Alright, so now if we measure this thing, let's see if it's 30 degrees. So here's 30, here's 35, go back 34, 33 degrees is right there. So that's exactly 33 degrees, okay? Now, what I gave you here in this triangle looks like it's a 90-degree angle here, right? And we can check it. Math, we're not really satisfied with looks like, so we do have a protractor here. Let's just measure this thing. Okay, so let's see if I can line this up. Vertex right here at 0, right? And then we've got, oops, got to rotate just a little bit. There's our 0 line. So yeah, there's our 90-degree angle, right? So this is a right triangle that I just gave us. And it kind of looks like these sides are the same length. So let's say that this is an isosceles because these sides are the same. Well, if that's 90, we know in an isosceles triangle, if we draw that perpendicular bisector of this third side, right, we have symmetry going on here, right? We have two reflected triangles within. This triangle here is the same as this triangle here. So therefore this angle right here must be congruent to this angle right here. So if this is a right triangle, we know this is 90, then the sum of these two have to be 90 because 90 plus 90 is 180. And if these two angle measures are the same, then they both have to be half of 90 degrees, right? 90 divided by 2. That's what this is, which equals 45 degrees. So whenever you have an isosceles right triangle like we do here, these angles right here are always going to be 45 and 45, right? 90 degrees, these have to add up to 90, and since it's isosceles, we know these angles have to be the same. Okay? Now let's go ahead and try to argue why the angles in a triangle add up to 180 degrees. So what I made here in GeoGebra, I just took a triangle, I measured the angles here, and then I took the angle measures and put them in this equation, so that if we add up the three angle measures, they're always going to equal 180, right? No matter what our triangle looks like. Okay? So if I stop, say right here, let's just add these up in our head real quick. 0.8, let's add up the place values here. 0.8 plus 0.2 makes 1. 1 plus 0.9, my bad, we're not going to use that example. Because I changed the rounding here. So let's do this one, sorry. 0.7 plus 0.3 makes 1, right? One whole number. Okay, so now let's add our ones together. So I'm going to add, we have 3 ones right here. I'm going to add that sum here, 0.7, 0.3, that made 1. I'm going to add that 1 to 3. So now we're sitting at 4. So let's add 4 to this 7. So now we're at 11. And 11 plus this 9 makes 20. So let's add that 20 to these 10s here. So we have 20, let's add the 20 to it. So we're at 40. 40 plus 100 is 140. And 40 plus 140 makes 180. Wow. Okay, calculators are way nicer. But show you that no matter what our triangle looks like, we will always have an angle sum. Look at this one. 8 and 12 is 20 degrees. 20 plus 160 is 180 degrees. Okay, so why does this always work here? Well, one way to prove this is a famous geometry proof here, is using parallel line relationships here. Okay, what I'm gonna do is I'm gonna make a parallel line parallel to one of these bases that goes through the opposite vertex. What I mean is, like, if I want to make a line parallel to this line, it would have to go through A. So I would have a line that's parallel to that going through A. I could make a line that goes through C. It would have to be parallel to its opposite side here, this BA here. So we could do a parallel line this way. I could do a parallel line going through B, and it would just be parallel to its opposite side here, this CA side. So for this example, I'm just going to pick one, and just know that I could have picked any point if I wanted to. So I'm going to pick point B here, and I want to go parallel to this base here. So I just constructed, using the parallel line tool, a parallel line to this side here. Okay? Now, I'm going to extend, I'm going to make this dotted here. I'm going to extend this base here. Okay? Now this looks a lot like our parallel lines examples that we've done before in the past. If these lines are parallel, let's think of this side BC as like a transversal, right? So if this is a transversal, this angle up here, doesn't it have to have the same measure as this angle here, right? Because they're alternate interior angles. So we did this in an earlier quest. I'm going to use my polygon tool, and I'm just going to make a triangle, because really I just want to encapsulate this angle here. And again, it doesn't matter where the points go on our rays, on our sides of the angle. It does not matter. This angle won't change. Okay, so now I'm going to grab my rotate tool. Oops, I need to find the midpoint of this segment, right? So I'm just going to click on it. There's the midpoint. I'm also going to do the same thing over here. I'm going to make the alternate interior angle to this green one. So I'm going to, since I have the midpoint tool, I'm going to make the midpoint there. Those midpoints have to be the center of our rotation, because this vertex, this point C, this angle C, has to rotate to this vertex here, right? So these vertices, since they're rotation points of each other, have to be the same distance from our center of rotation, hence the midpoint. Okay, so I got my rotate tool. I'm going to click on my polygon. I'm going to rotate it around point F. 180 degrees, right? C is going to map onto B, and that's a line, right, that goes through our center, our vertex. So it has to be 180 degree rotation. So I'm going to click, oops. Okay. Nope, I'm going to get my algebra window, make sure that I'm clicking on the right stuff here. I'm going to grab this rotate tool again. I'm going to grab my red polygon. I clicked on it in the algebra window. Now I'm going to click on my center, and notice we got that rotation. So this angle right here is really what I wanted to rotate. Those angles are the same, right? They're both 78.8 in this case. And the beauty of GeoGebra, no matter what my angle looks like, those angles are always going to stay the same, right? We rotated because those alternate interior angles are always congruent, right? So this angle here, plus this angle here, plus this angle, notice they're going to add up to 180 degrees. So if I can get this green angle to transform right here, then all three of my angles add up to 180 degrees, and that's what the proof is meant to show. So I'm going to make a triangle here. I'm going to make it green, just like this one. Okay, so here's my triangle just to encapsulate that angle right here. Okay, I'm going to click on my polygon, click on my center of rotation, 180-degree rotation, and notice that maps on perfectly. So this angle measure right here, make it green, it's got to be the exact same, because when we transform, nothing changes, right? Everything stays the same. It stays congruent and rigid, and those angles are the same. So this proof shows that if you add up the three angles in a triangle, this green angle plus this red angle plus this blue angle will always equal 180 degrees, and using parallel line angles, we can transform two of our three angles to make this linear. Be a linear pair, it'd be like a linear triplet, right? To make 180 degrees. So this is a famous proof that we did with GeoGebra. I hope that makes sense now, that the three angles have to add up to 180 degrees, right? Okay, so, whoops. Good luck with your guys' assignment. I don't think we have any more pages on this one. And be able to find missing angles in a triangle.